In this video, I'm going to go over the concept of supernodes in relation to nodal analysis. So there are two cases relevant to supernodes. The first case is when you have a voltage source between ground and a voltage node. So here you can see there's this voltage source right here, and it's connected between this nodal voltage V1 and the ground. So this case is really simple. All you have to do is you just set the voltage at that voltage node equal to the voltage source. So here we see the 10 volts is connected between ground and V1. So all we're going to do is say V1 equals 10. Then you just continue solving it like normal. So you first define all your currents. Then you do a KCL. Here, the only relevant node for KCL is V2. So we're going to say at V2, I1 equals I2 plus I3. Sum of currents going in equals sum of currents going out. And then finally, we're going to move on to the Ohm's law's equations. And we can easily see that I1 equals V1 minus V2 over 5, because it's where the current starts minus where the current ends divided by the resistor. And we do the same thing for I2 equals V2 minus 0 over 3, and I3 equals V2 minus 0 over 4. Now all that's left is to plug in the currents into the KCL. So we get the following equation. And then finally, we know that V1 equals 10. So instead of having V1 right here, we can just replace it with 10. So now we have one equation and one unknown. So this is the answer. You can solve that for V2 and you'll get the answer. Now next we have case 2. And this is when you have a voltage source between two nodes. So here you can see this 10-volt voltage source is now between V1 and V2. So here we're actually going to need to use what's called a supernode. So before we do that, let's first define our currents as always. So I'm just going to go ahead and do that real quick. All right, so now we have all our currents. And remember, the direction I chose is completely arbitrary. It does not matter. So now we're going to go ahead and place a supernode. So I like to just draw a dotted path around both nodes. And what we're going to do with that is we're basically going to perform a KCL of both nodes at the same time. So I'll draw a picture real quick to show you what I mean. Okay, so now we're just going to do a KCL following the same rules, except we're going to treat everything that's inside the dotted blue line as the node itself. So we're going to do a KCL at the supernode. And as you can see, right here we have an I1 going in, an I5 going in, and then both I3 and I4 are leaving. So our supernode KCL is just going to be I1 plus I5 equals I3 plus I4. And then we're going to continue the problem like always. So we're going to write another KCL for the other remaining node, which is V3. And that looks like I3 going in equals an I4 plus I5 going out. And then we're going to continue like normal. So next we need to do our Ohm's laws. So same rules as always. I1 is going to be start minus finish over resistor. Here this one starts at ground, so that's why it's 0 minus V1. And then same thing for all the other ones. Okay, and now we're just going to plug in all the currents into the KCL equations. So for the supernode equation, we're going to reach the following. And then we're going to simplify like always to get rid of these fractions. And then we're going to distribute. And then finally combine like terms. So that gives us our first equation. Now we do the same thing for V3 and simplify, distribute, and combine like terms. And that gives us our second equation. And you should notice that, wait a minute, we have 3 unknowns, but we only have 2 equations. So that means we need to get a third equation somehow. And the way we're going to do that is by, again, looking at this voltage source. Okay, so I'm just going to redraw it real quick. Okay, so we can develop a relationship between V1 and V2 only based off of this information right here. So basically, we can say that since there is a source between V1 and V2, it acts like either a voltage rise or a voltage drop. So the way you can look at it is by just pulling down this V1 and then looking at the polarity of the voltage source. That's very important. If you go through it from minus to plus, then it acts like a rise. So if we go from minus to plus, we're going to add 10, V1 plus 10 equals V2. And that gets us our third equation. Now, just as easily, you could have gone from plus to minus, and then you could bring down, okay, we're bringing down the V2. We're going plus to minus, so we're subtracting 10 and set that equal to V1. And you should notice that these are the exact same 2 equations, so it doesn't matter which one you use. I prefer personally to go minus to plus, so I always like to say like the V1 plus 10 equals V2. So that's the one that I'm going to use, but you could have used either. So now you can just bring that over here and rearrange it in the proper order. And our third equation will be V1 minus V2 equals negative 10. Now, if you can get this far, you have the answer. I actually went ahead and solved this, and you get V1, V2, and V3 all equal to 0. And all that means is when I made up this problem, I didn't pick numbers that produce a real solution. So that's my fault. But you can follow the process for any other problem. So now let's do a textbook problem, which will have actually real answers. So here we want to solve for V1, V2, and V3. So first we're going to define our currents as always. And now we're going to notice that we have two voltage sources between nodal voltages. And this is obviously a case 2, but it's two case 2s right next to each other. So if you have two voltage sources right next to each other, so if we follow the same thing we did before, we would say, okay, we're going to put a supernode between V1 and V2, and then, oh, we need another one between V2 and V3. So when you have this scenario, instead of doing that, you can just make one big supernode between the whole thing. So that's going to be our supernode here. And then we're going to continue as always with our KCl. So the only current going in is this I3 entering right there. So we're going to say I3 equals I1, and I2 are all exiting. And then I3 is entering and exiting. So we can include it on both sides, which means it's just going to cancel out. So we can rewrite this equation as 0 equals I plus I1 plus I2. And that's going to be our KCl equation. And you can notice how we don't have any more voltage nodes that aren't already part of the supernode. So that's the only KCl equation we can come up with. So we're going to move on to Ohm's law. And as always, we'll arrive at the following equations. And then now remember, every time you do a supernode, you also have to include your equations from the voltage sources. So just like the previous example, we're going to look at our nodes. Okay, we've got our V1, V2, and V3. Now, between V1 and V2, I like looking at it from minus to plus. So one of the equations will be V2 plus 25 equals V1, because we start at V2, pass through negative to positive, then we get to V1. Then we can do the same thing from V2 to V3. V2 plus, we're passing negative to positive through a 5I voltage source, equals V3. Except we already defined what I is, so we can rewrite this as V2 plus 5 times V1 over 2 equals V3. And then we'll arrive at our final equation, V2 plus 5 halves V1 equals V3. Now, as always, we can plug in our Ohm's law into our KCl. So if you do that, you get the following equation. So that's going to be our first equation. And then our second and third equations will just be these. So you can just rewrite them in the proper order. That will be our second equation. And then that will be our third equation. Then you can go ahead and solve this system using your matrix calculator, preferably. And you will get that V1 equals 7.61 volts, V2 equals negative 17.39 volts, and V3 equals 1.63 volts. And that is everything you need to know for supernodes. Just as a quick recap, you just follow the same rules for nodal analysis. You define your currents, do your Ohm's law, and if you have a supernode, make sure you get your equations from the voltage sources. Otherwise, you're not going to have enough equations to solve the system.